So we're very excited to have Nicolas Papernot. He comes from the machine learning community. I'm not an expert in machine learning, but I started learning from his papers. So we're super excited that he's here with us today. Let me introduce him briefly. So he is currently an assistant professor at the University of Toronto. He's also a faculty member at the Vector Institute, where he has a Canada CFAR AI chair. And also he's a faculty affiliated at Schroers Reisman Institute. And he works on security and privacy of machine learning. Also, he's a Conant researcher, and he was also a Google PhD fellow. And his work also received Best Paper Awards. And he also earned his PhD in Pennsylvania State University. And he also he was a research scientist at Google Brain. And we're very excited to have him here. I will repeat. So Nicolas, we can start.
Thank you, Antigone. I should start my talk with 3 disclaimers. The first one is I'm giving it from a poor internet connection, so feel free to interrupt me if the connection gets too bad. The second one is, as you said, that I'm coming from the machine learning community, so I do not pretend to be a crypto expert, and I'll try instead in this talk to give you flavors of problems that I think would benefit from more input from the cryptography community. And then the last one is that this is work that I've done in collaboration, including at the University of Toronto. So I indicate the title of the paper at the bottom of some of my slides so that you can reverse engineer who contributed to the work and credit them. So I wanted to start the talk by giving an overview of what I mean by trustworthy machine learning, because this is a term that is sort of used in many contexts. And so here I wanted to start with security itself, which typically comes in 3 flavors: confidentiality, integrity, and availability. And by now we've seen, we have enough insight to note that just like any other computer systems, machine learning systems are exposed to attacks under each of these aspects. So if we look at confidentiality, the model itself could be a valuable asset, especially when you're training it with a lot of data and compute resources. So I'll spend the second half of my talk discussing model stealing attacks and how we can defend against those. And we can think of these as sort of looking at the confidentiality of the model parameters themselves. The second aspect of security is typically integrity. And here we've seen a lot of work on both training time and test time attacks against machine learning. So at training time, we have attacks that fall under the spectrum of poisoning attacks, where one interesting result that I wanted to mention in my introduction is recent work by one of my visiting students, Ilya Shumailov, who demonstrated that it is not only possible to poison a machine learning algorithm's training procedure by inserting malicious points in the training set, but you can also achieve the same effect without inserting points at all in the training set. And so this is perhaps a little bit surprising, but the way that you can achieve the same poisoned behavior is by reordering the points which the algorithm is analyzing throughout training. And so I thought this was an interesting result because it shows that stochasticity in SGD, which is, I guess, the default optimizer to train machine learning systems, is very important if we want to have guarantees of generalization. And so this is a result that I encourage you to check out if you're interested in this line of work. Of course, at test time, we've also seen attacks with things like adversarial examples where the inputs are manipulated to force the model to make wrong predictions. I won't discuss those in the talk, but I'll use them as the motivation for one of my points being made. The third component of security is typically availability. And here for a few years, I thought that there were not very concrete attacks against the availability of a machine learning system. But it turns out that here again, one of my visiting students, Ilya Shumailov, found that it is possible to craft inputs that maximize the latency that the underlying hardware that accelerates a machine learning system will have when it processes that input, even at test time. And so in one of his experiments, what he found is, for instance, that you can take a model served by Azure for translation and increase the latency of its predictions by a factor of up to thousands. And so this is, of course, if you tie this back to the energy consumption that is increased by this latency, you can see the impact sort of on the carbon footprint, but also on the battery if the prediction is made on a mobile device. So this is the first component of trustworthy machine learning that I'll be discussing today. And then the second one is privacy, where instead we're looking at data sets that are sensitive, for instance, healthcare data sets, and we're training machine learning models based on these data sets. And so here we're concerned about potential leakage of private information contained in the data set. So I should preface the rest of the talk by saying that I will not be using private in the sense of private in the crypto community, but in the sense of differential privacy, which I'll introduce in just a few slides. And instead, I would refer to private in the sense of crypto by confidentiality. And so here in privacy attacks, what we observe is, for instance, that if we're able to observe as an adversary the predictions that a model makes, just the labels that the model predicts, then we're able to tell whether a specific point was included or not in the training set. And so you can imagine that if a model is trained, for instance, to predict when being part of the training set itself is potentially very sensitive. And so this is a result that my student Christopher published recently. So why is it hard to achieve trustworthy machine learning? I'm sure you've seen many of the papers that have been published on the topic in the last decades. I think the core problem is that we're missing definitions. And so I think this is one first example of where we can learn from the crypto community. So here I'm going to illustrate what I mean with adversarial examples, which are inputs that are crafted to force a model to misclassify the input. And so what you can see here, why do adversarial examples exist? Well, we're trying to learn this decision boundary here for the oracle. But of course, we're going to learn an imperfect decision boundary with our machine learning system. And so we're going to get this red dotted line here, which is not exactly the decision boundary that we wanted to learn. What this means is that if we take this image of a 3 here, it is located near the decision boundary. And what this means is that the model is too sensitive to small perturbations of its inputs. And so what the community has done, the machine learning community and the security community has done, is try to produce training procedures that can provably demonstrate that the classifier is constant around its training inputs. And this is proposed as a way to achieve robustness to these adversarial examples. And so you can see here on the right, this is what we've achieved. And the community has published a number of approaches to do this, where we now have this black dotted line that is the machine learning model that we've trained. And you can see that it has shifted compared to our red dotted line, which means that now when we look around the training image of the 3, all of the points that are within this ball here are classified in the same class. And so this looks like we've made progress in terms of robustness because we now have this classifier that is less sensitive locally. The problem here that you may have noticed is that we haven't said much about how we define this ball. And so in practice, the way that we do it is by using a p-norm. And so the reason we're using p-norms is we don't have a computationally tractable way of defining what is the neighborhood of each of these training images. And so we're going to approximate this neighborhood using a p-norm. The problem is that what this means is that the norm does not reflect the underlying semantics of the task. And so if we look here, what this implies in practice is that we can take this image of a 3 here and find images within the ball that has been certified to be robust for the classifier that are from different classes. And the classifier will predict the label 3 for this image here, for instance, of a 5, because it is close under this P norm. Of course, you as a human know that these are semantically very different inputs, but here this shows a discrepancy between what the classifier has learned and the underlying semantics of the task. And the problem here is that we're using an approximation, the P norm, to define what we mean by trustworthy predictions in this case. And because this definition is incorrect, we're introducing a necessary trade-off between the accuracy of the model and the robustness. And this means that we are going to always have an arms race where here we had an initial vulnerability that led us to introduce this P norm-based robustness, which we've now been able to address, in this case on the right. But because of that, we've now introduced new forms of attacks against this classifier, which are now exploiting this excessive invariance. And so this is a result we discuss in this paper, which shows why we're never going to be achieving a robust classifier using P norm approximations for robustness. And so this is sort of an example that brings up this question, which is whether machine learning systems allow us to approach security and in general trust in a way that is different from real world computer security. So if we look at computer security and particular system security, this offers where we balance the cost of protection with the risk of loss. And so this means that we don't have provable guarantees. And so we could ask ourselves, are machine learning systems in some sense, quote unquote, doomed to have this similar arms race? And in this talk, I'd like to give a few examples of why I think this is not necessarily the case. And I usually say that a good example is that machine learning systems are very amenable to crypto-like treatment. So I think this will resonate very well with this community. And I hope that the presentation will give you ideas for future work to work on in this direction. So the first part of my talk, I'm going to discuss data privacy as an example where the definition of what we mean by trustworthy machine learning is very clear and has allowed us to achieve principled and systematic progress towards improving the privacy of machine learning. And the definition is most likely very familiar to many of you because it comes from cryptographers. And the definition of privacy that is the consensus now in the machine learning community for private data is differential privacy, where the idea is that we have an adversary that is observing the output of our randomized algorithm. And the adversary should not be able to tell whether the algorithm was operating on either of these two data sets, where the data set at the top included the record for one particular individual, whereas the data set at the bottom is identical to the exception of that record, which has been removed or altered. And so what this means is that we're able to prove that the behavior of the algorithm is statistically indistinguishable on these two data sets. So the adversary is not even able to infer whether the person contributed the record or not, and so whether they existed. So this provides them with privacy. And so the way that we, in practice, measure how private an algorithm is by analyzing it in order to prove a bound on the indistinguishability, which is defined as follows, where we're looking at the probability of the algorithm operating on this first data set D, making a certain output, being close to the probability of the same algorithm operating on the second data set D prime, making that same output. And so this has to be proved for all possible outputs and all pairs of data sets D and D prime that only differ by one training record. So once we have this, basically our goal as machine learning researchers and privacy researchers is to decrease the bound so that we have a tighter upper bound on the indistinguishability that I just described. And so there are many ways that we have come up with to train machine learning models with differential privacy. One of them is called differentially private stochastic gradient descent. Here I'm going to introduce another one called Pate because it allows me to illustrate why differential privacy is such a good fit for machine learning, and in particular, how well it aligns with generalization. So if we take a look at this diagram here, what I'm showing is that in order to achieve privacy, we're going to take our sensitive data and partition it in n different subsets. So this is a mathematical partition, so there is no overlap. And then from each of these partitions, we're going to train a machine learning model. And so there are no requirements on how we train this machine learning model. The only constraint is that it has to be trained independently. And what this means is we now have an ensemble of n different models that are all trained from different subsets of data, but that all perform the same task. And so how do we have these models predict with privacy? Well, the naive thing to do would be to say, well, I'm going to take the argmax and ask each of these different models to predict a specific label. And then I'm going to take the label that was the most commonly predicted. This provides an intuitive notion of privacy, because if multiple teachers make the same prediction, then you can understand why this prediction is not specific to any of these individual subsets of data. And so if my training record was in this initial data set, it's only going to be in one of these subsets of data, so it only influenced one of the teachers. The issue with this and why it does not provide differential privacy is that, for instance, if you have two labels that receive the same or almost the same number of votes, then one teacher changing their prediction from one to the other label can change the overall outcome of our aggregation. And so this is private firms. The way that differential privacy is by randomly perturbing the histogram before we output the argmax. And so this provides us with a noisy aggregation mechanism that is differentially private. We can think of this as a differentially private machine learning API. The one catch with this is that every time that we make a prediction, the privacy budget that is expended is going to increase, because we're bounding but not making null the privacy leakage that is happening for each answer that we're revealing. And so we have to essentially take these differentially private predictions and use them to train an additional model here, which is the student model, which will then be used to make predictions in the end. And so what this means is that we transfer the knowledge from this ensemble into the student model with privacy guarantees. And once we've trained the student, we can delete all of the teachers and even their training data, and the privacy budget is fixed at that point. So why did I introduce Pate? The first reason is, if we come back to this, is that you can see there is a strong alignment between privacy and generalization in this setup, because the more teachers agree on the prediction that is being made, the more this prediction is likely to be correct, because it's been made independently many times. So this is good on the machine learning perspective. In terms of privacy, the more consensus we have, the more private the prediction can potentially be, because we can introduce more random noise before we take the argmax without perturbing the correctness of the argmax mechanism. And so what this means is that in cases where consensus is strong, we can get improvements in both the accuracy and the privacy, which is very unusual in computer security, where you have an alignment in the security constraint and the performance objective. And so this is, I think, one of the reasons why differential privacy is such an exciting area of research in the context of machine learning. Another practical reason is that with differential privacy, we get provable guarantees, which are robust to knowledge that the adversary may acquire in the future, or new capabilities that the adversary may gain. So if you recall the example that I gave with adversarial examples research, one problem with many defenses proposed against adversarial examples is that they do not model an adaptive adversary that will actively seek to evade the defense. So for instance, because adversarial examples are found typically by performing a gradient-based search, many defenses perform an instance of the following here, which is to basically mask the gradients around inputs that the model will predict for, so that someone trying to find this step function here is not going to be able to, because the gradients are not indicating where the step function is. And so when you have such a defense, you can perform, for instance, a black box attack by taking another model and then finding adversarial examples for this model and then transferring them to the defended model. And so this is why sort of this class of defenses is not effectively bringing you any robustness. In contrast, in privacy, there has been similar defenses proposed with something called membership inference attacks, which is something that I introduced at the very beginning of my talk. So if you remember, what I said is that membership inference attacks is possible only by accessing the label that the model is predicting. And so what this means is that defenses that previously tried to make membership inference harder by masking the confidence of the model, which makes it easier to tell whether the point was included in the training set or not, are now easily defeated by a label-only membership inference attack. And so what we see here on the right is a result by my student Christopher, where what he found is that previous attacks that required confidence access perform just as well as his label-only attack. So what this means is that all defenses that are relying on the fact that they're hiding the confidence of the model or randomizing the confidence of the model are basically trivially defeated by this attack, which does not rely on the confidence and performs equally well. Whereas instead, if you train the model with, what we found is that this is the only approach to defeating, at least partially, this label-only membership inference attack. And so you do get an improvement in the privacy that is robust to the developments from the attacker side. So I think this is very, very strong advantage, again, of training with differential privacy. Another reason, oh, absolutely, yes.
Does it depend on how many queries you do when you train with differential privacy? So it defeats it based on how many?
What do you mean in terms of for the attack?
Yeah.
Yeah, so basically what happens with differential privacy is that the smaller the epsilon you're able to achieve during training, the lower the advantage of a membership inference attacker will be. So if you don't have differential privacy, you'll have better than random chance ability to guess whether a point is in the training set or not. And as you improve the differential privacy guarantee that you're able to achieve, you're going to bring that attacker closer to random guess, basically a 50-50, for instance, if you have a baseline of 50-50 being in or out of the training set. Does that answer your question?
So you're saying that it all depends on the parameter epsilon when you train with
that's right. That's right. That's right. And that parameter typically trades off with performance. Eventually, if you prove an epsilon that is very small, you're going to have to pay a price in terms of the utility of the model.
Based on the other attacks that you were comparing in the graph, so the epsilon that you were using was giving good accuracy, or was it like?
Yes. So basically, what we're showing in this graph is that the approach where you train with differential privacy is able to achieve the best trade-offs between improving the robustness to the attacks and maintaining a good accuracy for the model that you're training, so that it can predict in a useful manner. So this is what we're showing here in this box.
Okay.
Yeah.
Great, thank you.
Yeah, thank you for the question. So one other reason that I wanted to introduce Pate is that we've recently extended our work on Pate to include a possibility of performing Pate in a distributed setting. And this is, I think, interesting to this community because it relies on cryptographic primitives. And so the observation here is the following, is that if you look at this setup here, we've manually partitioned the data into multiple partitions. Whereas you could imagine setups where this data would already be partitioned sort of organically. So imagine, for instance, if you have a network of hospitals, they might each have locally a training set, and they might have already trained their own model locally, but they could benefit from inferring jointly at test time because, for instance, a specific hospital is lacking training data for a specific test point. And so this is what we've done here in Capsi, which is to combine Pate to get a differentially private prediction with cryptographic primitives to be able to perform this prediction in a distributed setting without revealing information about the models or the test points that are being predicted on. And so the way that this works is that you have one of the hospitals in the example that I just gave, that is the querying party, and has a test input that they would like other hospitals to predict on. So what they're going to do is encrypt this point and send it to the other hospitals, which are going to infer on the point using homomorphic machine learning so that they can produce a logit vector without being able to read the test input, and without having to reveal their own machine learning model to the hospital that submitted the query. Once they've done that, we use secret sharing between each of the answering parties and the querying party. So we have a two-party protocol that allows us to basically turn these logits into one-hot vectors, and then to reconstruct the histogram that we described, where the answering parties is submitting a vote for which class they think the test input belongs to. And so once we've done this, we're going to submit each of the answering parties' shares to a central party, which is going to aggregate the votes from the different individual hospitals and then perform the summation operation that is required to reconstruct the histogram, and also add the random noise that is required to obtain differential privacy. And so what this means here is that once the central party has performed this summation and noising of the votes, it can perform one last two-party protocol with the querying party to reveal to that party the aggregated label that the teachers have predicted, the different hospitals have predicted. And so what this means is that here in this setup, the querying party does not learn anything private that is contained in the answering party's training sets, because we've produced this prediction with differential privacy. The querying party also does not need to reveal their test input to the different answering parties because we've used homomorphic machine learning. And the answering parties do not have to reveal their models to the querying party. And finally, the privacy guardian does not learn anything about the test input that was submitted, but also about the individual predictions that the models are making the answering parties. And so we think this is an interesting setup in setups where we have an heterogeneous set of participants that each have different models, all performing the same task. And these models already exist, and all we want to do is to predict jointly as an ensemble. And so this is a very different setup from federated learning, where instead you have to assume that everybody jointly trusts each other to be able to train a single machine learning model centrally. Here, all of the models remain fully distributed and owned independently by the different participants. And of course, each participant can alternate roles and be a querying party in one of the following realms of the protocol. And so what this means is that as a participant, you can perform something like active learning to improve your own local models predictions by integrating the predictions that Capsi is providing you. Our protocol is called Capsi, to improve your training set locally and then to fine tune your model. And so in particular, what we found is that if one of the participant is lacking data for a specific subpopulation in the training set, then this can allow them to improve the fairness of their classifier by participating in this protocol. And so if you're interested in this, I recommend checking out the paper, which is called Capsi Learning. And essentially, you'll see that there is a lot of opportunities for cryptographic improvements of the protocol. In particular here, as you've noticed, I've assumed the existence of a central party. So it would be interesting to have an alternative to this protocol that does not assume trust in this third party. And of course, the homomorphic machine learning component of the protocol is a computational bottleneck in terms of the performance of the end-to-end protocol. So that's always something that we could benefit from progress. Okay, so again, I just want to pause here to remind you of sort of the different reasons that I've mentioned differential privacy being advantageous in machine learning. And the first one is that there is not a necessary trade-off between the privacy and the machine learning objective. While it is true that there is often a trade-off between privacy and the accuracy of the model, it's not fundamental. We should be able to achieve both simultaneously. And what we see in practice is that we have a degradation that is smooth when it is not possible to learn something privately. And in particular, I'm now going to give you two examples of when differential privacy is not a silver bullet. The first one is machine unlearning, where instead we're trying to delete a training point from the machine learning model. And so this is a very difficult problem that comes up for the first one is reasoning attacks. The second one is laws like the GDPR, regulations like the GDPR, which encourage users to basically request the deletion of data that they've previously allowed a company to use. And so here, differential privacy is not a silver bullet, because in differential privacy, you're bounding the contribution of each training point. Whereas in machine unlearning, you would like to make the contribution of a specific point be 0. So not only you want a bound that is 0, but you want that bound to only hold for a specific point. Whereas in differential privacy, you want that bound to hold for any possible point. And machine unlearning is very difficult, in particular in deep learning, because it is very difficult to estimate the influence of each training example in the final model. And so this is for many reasons. The first one is the stochasticity of the training procedure in the way that data is sampled, but also the objective itself having multiple minima. But the second one is the nature of the algorithm being iterative during training, which means that the recursion means that we have this incremental learning procedure that is difficult to analyze the influence of each training point in the final model parameters that are learned through the incremental procedure. And so this led us to basically observe that we won't be able to achieve machine unlearning through differential privacy. And instead, we have to look at a slightly different definition of what it means to unlearn, which is that we want the distribution of models that we can learn from a data set D to be the same than the distribution of models that we would achieve by first learning on this data set combined with a particular point, and then unlearning from this point to basically remove it from the training set. So what this means is that by learning and unlearning, you get the same distribution of models than if you had learned in the first place without the specific point to be unlearned. And so this is a very strong guarantee, because what this means is that you could have obtained the model here that you have on the right, which has been obtained by first learning and then unlearning. You could have obtained that model directly by performing another round of training from scratch from the original data set that did not contain the point to be unlearned. And so this is very difficult to achieve, again, with things like deep neural networks. And so the way that we propose to achieve this definition of unlearning is to introduce two knobs in the way that machine learning models are trained. And I'm going to discuss this very briefly because I want to leave time for another topic. But the idea is to say there are two issues with stochastic gradient descent. The first one is that we are analyzing the entire training set at each epoch, which makes it very difficult to tie back the contribution of a specific point into the model parameters that we're learning. So what we're going to do is reorder the way that training points are analyzed to first learn from a subset of the data. So let's say we learn from 10% of the data. Then we can save the state of the model and then introduce an additional 10% of the data, and then save again another state of the model, and then continue introducing data until we have analyzed the entire training set. What this means is that once we want to unlearn, we can now trace back the point in time where we introduced the specific point to be unlearned, and then we can recover the checkpoint that did not contain the training point in particular, and we can resume training from that checkpoint. And so in expectation, we're going to get an improvement in how much work we have to do to retrain the model. Another problem with stochastic gradient descent is that a specific training point influences the entire model parameter vector. So a point may contribute to an update in all of the different parameters. And so what we propose here is to again use the same intuition behind Pate, and to, instead of training one large model from the entire data set, we propose to train an ensemble of models. And what this means is that we're training smaller models from disjoint partitions. And so if we want to unlearn a specific point, we need to retrain the model, then train one single large model from scratch. And so if we combine these two knobs, what we find is that by reordering the data and also partitioning the data, we're able to effectively retrain the model as if it had been retrained from scratch, and to get this equality of distribution of models that I just described at a much smaller price in terms of computation than if we had to retrain the entire model from scratch. And so here, I think this is an example of where the definition of differential privacy is not an ideal fit for this flavor of privacy, but I think here there is work to be done in sort of improving this definition here that I presented, which is very crude and very difficult to achieve, so that we can propose mechanisms that more effectively unlearn, even more effectively than this mechanism here. The second reason why differential privacy is not a silver bullet is that it introduces a trade-off with fairness, where in data sets where you have a heavy tail, such as medical data sets, the privacy will prevent you from learning from tails of your distribution, for which you have very few examples of. Whereas fairness will ask you to have good performance on these tails of the distribution. And so what this means is that as you increase the strength of the privacy guarantee, you're degrading your fairness criteria. And so this is something fairly fundamental to certain data sets. And in particular here in this research, we found this is consistent across several medical data sets. And so I think here that we need to have more work to understand how we can adapt the definition of what we mean to be private to this simultaneous fairness criterion. And in particular, we have to visit ideas where we are going to provide guarantees that are specific to different points in terms of the privacy, which is of course a difficult question to navigate, in particular because it raises ethical concerns. So I think one of the conclusions here is that we need to do a lot more work aligning machine learning with human norms. And I've discussed privacy and fairness in this first part of the presentation. But I think in general, there is a need of better definitions like differential privacy that align with the goal of the machine learning community, which is to produce a classifier that generalizes well. And so this is work where I see a lot of opportunities, in particular because the community at the intersection of machine learning and security is treating each of these problems independently. So some people are working on privacy, some people are working on fairness, but we're not capturing the overall trustworthiness of the classifier. And there are tensions that will be very difficult to resolve if we don't incorporate this thinking ahead of time. The last part of the presentation, I'll try to finish in the next 10 minutes or so, is fairly different and is going to discuss what I think is another problem space where cryptographers can help us in the machine learning community, which is the question of model ownership. And so if you recall, in the very beginning of the presentation, I discussed model stealing attacks where an adversary that has access to the predictions of your model is able to extract a copy of that model if they have unbounded query ability, right? This is pretty intuitive. If you have a function, if you can ask what the value of that function is for any point of your choice, eventually you can recover an approximation of that function. And so here, this is a pretty fundamental problem in machine learning. And in particular, progress in machine learning, in learning from little supervision, has made model stealing a lot more efficient. What this means is that it has made the query complexity of model stealing a lot lower. And in particular, there's an area of machine learning research called semi-supervised learning, where the goal is to learn from partially labeled data rather than fully labeled data. And so this facilitates model stealing attacks. And this is something that one of my interns, Matthew, showed, because once you have an unlabeled set of data points, you only need to have the model that you would like to steal label a subset of these points. And so what this means is that you can achieve computational while making much fewer queries to the model that you're trying to steal. And so this is just making it model stealing attacks easier. Another reason is that machine learning researchers are more and more relying on large pre-trained models to produce models for specific tasks. So you've most likely seen developments around GPT-3, for instance, as a language model. And so a lot of models are being fine-tuned from these large pre-trained models. What this means is the adversary has knowledge about all language models that are produced, because the adversary knows that if they start from this initial checkpoint, they're more likely to achieve a model that is similar to the model that they're trying to steal. And in particular, what this means is that you can steal machine learning models with purely random queries that are not from the data distribution that the model has learned from, which is pretty surprising. And this holds for language because of this pre-training aspect, but it does not hold for vision, which is something that I was surprised. And so in practice, what I want to get across here is that it's impossible to prevent model extraction from happening, because if you want to reveal the prediction that the model is making to your legitimate users, there's no way that you can prevent the adversary from using that information to recreate the model locally. And so what we've been working on in my group is post hoc approaches to preventing model stealing. The first one is to detect whether a model is stolen or not. And so this is something we call dataset inference, where we flipped around the idea behind membership inference attacks to the advantage of the model owner. And so the idea here is that someone trying to steal your machine learning model is trying to derive knowledge that was contained in your training set. No matter how they steal the machine learning model, they could use a very simple attack. They could use some of the more sophisticated attacks that I just described. What they're trying to get at is that you have training data that they do not have access to, and they want to learn from that training data. And so what this means is that a useful stolen model will contain secret information that was contained in your training set. And so as a model owner, if you suspect someone has stolen your model, what you can do is take your training set and query the stolen model with these training points. And what you will notice is that when the model was indeed stolen, it will produce predictions that reveal that your training data is a member of that model's training set. And so what this means is that you can take a few of your training points, for instance, use the label-only membership inference attack, which consists in querying the model, and you will essentially get an undeniable proof that this model contains the same information than your training set. And what's interesting there is that in the context of privacy, it's difficult to infer membership reliably because you're trying to infer the membership of an individual training point. Whereas here, in this context, you have access to the entire training set. So you can take the leakage, the privacy leakage from individual training points and aggregate this leakage over multiple training points until you have enough confidence that the model was indeed stolen and trained from your training data. And so this is something that we've presented earlier this year. And basically, I think this is very interesting because it's a rare example where we're providing an asymmetric advantage to the defender. Because the defender has access to the training set, they have more information than the adversary here. And in particular, they can detect the attack fairly easily without revealing much of their training set. We found in particular on a couple of data sets and models that only revealing 50 of your training points was enough to get below a 1% false positive rate in detecting that the model was stolen. And so I think this is an interesting example where we flip a privacy attack and use to something that comes up a lot in serial machine learning research. The other approach that I want to discuss before I conclude is called proof of learning. And so here the idea is motivated by model stealing, but it's a little bit broader. And I think there are a lot of open problems that would be very interesting to solve. The idea here is to say, we'd like to obtain a proof that we've trained a particular machine learning model. And so this is a proof that we could use to claim ownership for that model, but also just to prove that the training procedure was run with correctly. So basically to prove the integrity of the training procedure. And so the idea here is to observe that training deep neural networks accumulates secret information organically because of the stochasticity of gradient descent. And so it's very hard, for instance, to reproduce twice the same machine learning model, even by simply repeating the exact training procedure on the same training set. And so what this means in practice is that each training run accumulates some secret information from the stochasticity. And so what we proposed here is to say, well, if we would like as a model owner to provide a proof to a verifier, which could be, for instance, an auditing, a regulator, for instance, that is auditing us and trying to assess whether we indeed trained that model or not, then what we can do is we can reveal information from our training run, secret information from our training run, to prove that we have indeed performed that training run correctly. And in particular, what we found is that we can reveal information about the data that was sampled at each of the training steps, so each of the steps of gradient descent, and as well auxiliary information to seed some of the randomness that will be introduced by stochastic gradient descent, so that the verifier can take the checkpoints that we produce during training and verify some of the steps of the gradient descent to assess whether we've trained the model indeed correctly with some degree of certitude. And so the information that we log in this proof is the following. We have the model weights, which is organically saved as the checkpointing procedure for all machine learning frameworks. To this, we add information about the data that is sampled at each of the training steps, so the indices of the training points. We also include the signature of these training points because we want to be able to commit to a specific training set and then we want the verifier to be able to assess that we indeed use these specific training points. And then we include auxiliary information, which is essentially hyperparameters of the training procedure, which are important to be able to, again, make the training procedure as deterministic as possible once given access to that information. What we do then as a verifier is the following. The first part is to verify the initialization of the model, because a training run is produced from two possible initialization, either a random initialization, which we can assess whether a particular model parameter vector is random or not, or the training procedure is going to be initialized from a pre-trained model. In this case, we can simply ask the model owner to produce a proof of learning for that specific pre-trained model, or to explain how they got access to that model, that pre-trained model. So you can see there is a recursive aspect to this, which is very interesting. Then what the verifier will do is verify the entire training sequence. Of course, you cannot verify the entire training sequence in a single shot, because as I just explained, the stochasticity will lead you to a very different model parameter state at the very end of the training procedure. So what we observed in this paper is that we need to verify individual steps of the gradient descent, so that we're able to reproduce these individual steps accurately enough that we are able to recover the parameter of the one produced by the model owner. So once we do this, we're able to take some of the gradient descent steps, which we select by their magnitude. And as a verifier, we're going to select these gradient descent steps, look at the auxiliary information produced in the proof, reproduce the gradient descent step, and then assess that it is indeed close to the one provided in the proof of learning by the model owner. And if we get a result that is close enough, then we can validate the proof of learning. And so the model indeed belongs to the model owner, and the integrity of the training procedure is verified. Here, there are a couple of interesting things from the security perspective. The first one is you could wonder how an adversary could spoof this verification. There is difficulty in spoofing the proof of learning because of the computational cost. And so you could do many things. You could try to produce a cheaper proof of learning without actually training the model. And what we've done is we've looked at a series of strategies for doing that and showed that they can fail. Essentially, because of the inherent cost of training the model and producing the proof. What is important to observe here is that it is difficult to invert a training procedure, because if you want to invert the training procedure, you will have to do at least one forward and backward pass in your training algorithm, which will be at least as expensive as training itself. And so this is what we observe here in practice. We looked at several strategies. One of them is fine-tuning from the final checkpoint that the model owner has released. And this does not pass the initial verification step that I've described. Another one is concatenating two valid proof of learning sequences to produce one that leads to the model that you'd like to incorrectly claim ownership to. This does not work because of the fact that we verify the largest updates, and essentially the concatenation step will be flagged through that process. And so I'm not going to go into the details, but basically this is interesting because we're observing that the inherent stochasticity of the training procedure produces a proof that we've trained the model correctly and that we are the correct owner of this model. There are some aspects that I think we would benefit from help from the cryptography community. The first one is decreasing the storage cost and the computational cost. Here, the procedure that I've described depends on a number of things, the storage and the computational cost, but primarily the problem is that it's very difficult to store efficiently a differential checkpoint of the model throughout training. The second issue is that the computational cost includes reproducing some of the gradient descent steps. And so this is inherently expensive. And so we would benefit from input from, for instance, techniques from zero knowledge proofs to allow us to verify these steps without rerunning them in practice. And then the last part, which I think cryptography can help, is understanding the sources of randomness in training machine learning models so that we can better control them when we're verifying these proofs of learning. Okay, so this concludes my talk, and I hope that despite the very diverse array of topics, I've identified a number of opportunities for input from cryptography. In particular, I just want to summarize that I think there are opportunities in data privacy going beyond definitions like differential privacy, in model ownership, and just as I was talking about training time, integrity verification. I think there's been a lot of work in the cryptography community in verifying machine learning computations at test time when making predictions, but very few at training time when producing model parameters. And I'll conclude by saying that I think trustworthy ML research is very exciting because it allows us to better understand why machines to generalize. And so I think there are many opportunities to simply improve how we train machine learning models by looking at their security. And so this is one of the reasons why I'm very excited to look at the area and what results we're going to be producing. Thank you for your attention. I'll be taking questions if we still have a few minutes.
Thanks a lot, Nicolas. These are very and super interesting problems. And we don't have a lot of time for questions, maybe for some quick questions. If somebody has any question, please either speak out. Daniel, yeah, go ahead.
Yes, thank you, Nicolas. I just wanted to ask you a quick question. It was a great talk, by the way. Just when you describe the solution for avoiding model stealing, right? Which is if you steal the model, then I can try to check if someone steals it, right? And the solution is interesting because it basically turns an attack, which is a membership inference attack, into a defense, kind of, right? Because what you do is that you run but then I wonder if there are defenses against membership inference attack, then the attacker can use the defenses to defend against the defense, right?
Right. Yeah, so this is the interesting part about it, is the asymmetry between the attacker and the defender here that I was surfacing. Because if you have a defense against membership inference, you will not be able to decrease the privacy leakage to 0. So you're going to, for instance, if you train with differential privacy, which is, I guess, the defense that I presented as being the most efficient against membership inference, essentially what you're going to do is you're going to bound the privacy leakage, but you're not going to make it 0. And so what this means is that membership inference will be harder for individual points. So it will be harder for an adversary to guess whether the point is part of the training set or not, but it's not going to be completely, basically it's not going to take the advantage of that guess to a random guess. Does that make sense? And so if you take multiple training points and you repeat the membership inference procedure, even if you're slightly better than random chance, you're going to accumulate this signal across multiple points. And so if you reveal enough of your training points, then you will be able to get to a point where the dataset inference is sufficiently confident. Does that answer your question?
Yeah, it does. So the owner of the data has more power basically to carry out like a more powerful.
Yeah, exactly. Because in a privacy attack, you care about a specific point, a single point, whereas as a dataset inference, in dataset inference, the model owner has multiple points, and they can reveal. They don't want to reveal their whole training set, obviously, because that would defeat the purpose. But even if they reveal just a handful of training points, then they'll get enough confidence by aggregating the membership signal across these multiple points.
Well, that's great. Thank you so much.
Yeah, thanks for the great question.
Yeah, unfortunately, we're running out of time. If somebody has any questions, please email Nicolas. I will also email you. I have some questions. And thank you so much.
Excellent. Thank you again for inviting me, and I look forward to questions over email.
Thank you so much.
Take care.
You too.